Hello, everybody. Welcome to my talk about C++ standard parallelism. I'm Bryce Adelstein Lelbach. I work at NVIDIA, where I'm a principal architect. I work on HPC and quantum computing programming models and compilers. I'm also the chair of the Standard C++ Library Evolution Group, which designs and standardizes the C++ standard library. I also chair the American Committee for Programming Language Standards, and I serve as the editor for the American Inclusive Terminology Guidelines and Standards. So today, I'm going to talk to you about the C++ Committee's plans for bringing parallelism, asynchrony, and accelerated computing into standard C++. So first, a few conventions that are going to be used throughout these slides in the interest of brevity. We're going to use these namespace aliases throughout the talk because nested namespaces are just a little bit too verbose for me. So std_v for std views, std_r for std ranges, ex for std execution, and this thread for std this thread. This talk also makes pretty liberal use of class template argument deduction, or CTAD. So standard C++ has always had support for deduction of template arguments when calling a template function. Everybody's probably pretty familiar with that. But in C++ 17, we extended this to work for class templates when calling their constructors. So for example, when constructing a tuple, I don't need to spell out what the types are. They can just be inferred from the arguments. And likewise, when constructing a std array, the element type and size can be inferred. So the basic premise of this talk and the basic premise of our strategy for parallelism in C++ is that the barrier to entry for parallel programming is far too high today. We live in a world where almost all hardware platforms are parallel and require explicit programming to utilize that parallelism. And despite that, many users and many code bases do not utilize parallelism, and those that do, many of them have chosen approaches that are not portable to accelerators such as GPUs. And so, the C++ committee wants to build an on-ramp to parallel programming. We want to give users easy-to-adopt solutions that are going to be universally portable. We're not aiming to expose all the capabilities of each platform or even to necessarily let you achieve 100% of the performance possible on that platform. We want something that's going to be portable, that's going to be good enough in most of the cases, that's going to help you get onto the accelerated computing highway. And maybe there will be some small places in your code, some key kernels that you'll need to write something platform-specific for. We really want widespread adoption and normalization of parallelism across the C++ ecosystem. So there's three pillars to our strategy for parallelism in standard C++. First, we need a corpus of common algorithms that will dispatch under the hood to vendor-optimized parallel libraries. And then next, we need tools that will let us write our own generic parallel algorithms that are parameterized on where they run and thus can run on any type of execution context. And then finally, we need some asynchrony mechanisms. We need some facilities for composing parallel invocations together into task graphs. So we're going to start off by talking about this first pillar, the collection of common parallel algorithms. So C++ has had a set of serial algorithms for manipulating sequences of objects since the first standard. These algorithms operate on one-dimensional sequences. Initially, they were parameterized with pairs of iterators, but with C++ 20, we've introduced a new, more powerful abstraction, ranges. So we have about 100 different standard C++ algorithms. There's for loop abstractions, there's filters, sorts, searches, rotations, reductions, scans, etc. In C++ 17, we introduced parallel versions of these algorithms. The parallel overloads have the same interface as their serial counterparts, except that they take an additional parameter, an execution policy, and that describes what form of parallelism is allowed, if any. Execution policies describe the how of execution, but they don't specify the where. So that's left completely up to the implementation. The execution policy parallelism, it could be implemented with a variety of different strategies, such as a bespoke CPU thread pool, OpenMP, GCD, or GPU acceleration, as is the case on NVIDIA platforms. Execution policies permit parallelism, but they do not require it, so an implementation may choose to not parallelize. These execution policy overloads are all fork-join synchronous, so the implementation will wait for the parallel operations to complete before returning from one of these algorithms. There are 4 execution policies in the standard. Seek indicates that all operations must be performed within the calling thread and must be indeterminately sequenced. So basically it says no parallelism is allowed. Unseek also requires all operations to be performed in the calling thread, but allows those operations to be unsequenced with respect to each other, and so that means that vectorization is allowed but not required. Now, par allows the implementation to parallelize operations at its discretion. It does not require parallelization, it simply allows it. But it also requires that all operations within each thread be indeterminately sequenced, so that means that vectorization is not allowed. So par unseek allows operations to occur in multiple threads and to be unsequenced with respect to each other, which means that both thread and vector parallelism is permitted. So again, this means parallelism is allowed, but not required. The implementation may choose to not parallelize. So we're gonna look at this example of a parallel word count. So we're gonna write this with a single parallel transform reduce. So transform reduce takes 2 operations, a transformation operation and a reduction operation. And what it does is that it applies the transformation to the inputs, and then it uses the reduction to sum the results of those transformations. So if you're familiar with MapReduce, this is C++'s version of it. So we're going to use the overload of transform reduce that takes 2 input sequences and a binary transform function. The first input sequence is going to be the entire string except for the last element. The second input sequence will be the entire string except for the first element. So this means that our binary transform function will be passed a window of every 2 adjacent characters in the string. So our transformation function's job is to tell us whether the 2 adjacent characters that it's looking at are the beginning of a word. So if the left character is white space and the right character is not white space, then the right character is the beginning of a word. So the pseudo sequence that's going to be performed by the transformation, that will be produced by the transformation, will look like this. For every word, one and only one of the transformation invocations is going to return true. But what about the first character of the string? We never actually test it with our transformation function because we start at that second character. And so we need to account for that first character because it might be the beginning of a word. And we do that in the initial value for the reduction. So our reduction operator is just std plus. So after that transformation, what we have is this pseudo sequence of bools. And so just summing up that sequence into an integer will give us the word count. So this is standard C++ code. It's parallel, it's portable. You can run it anywhere, on your GPU, on your server CPU, on your laptop, on your phone, on your watch. So in C++20, the standard library introduced ranges. And unlike iterators, ranges are designed to be composable, and they can be lazy. Ranges allow us to express a wide range of algorithms in terms of a few key primitives. And used in conjunction, C++20 ranges and the C++17 parallel algorithms can be quite powerful. So let me show you a few examples of that. So standard C++ algorithms iterate over sequences of objects, for example, the elements of a container. However, sometimes we want to iterate through indices instead of objects. This is particularly important in numerical and scientific computing. We can do this using IOTA, which is a range factory that was introduced in C++20. So it produces a range of monotonically increasing integers. For example, IOTA of 1 to n will produce a range of all integers from 1 to n minus 1. This is similar to Python's range function. So instead of passing iterators to a container to a parallel for each, we can instead pass an iota range, giving us a parallel for over indices instead of objects. We can also use parallel algorithms and ranges to iterate multidimensional index spaces. C++23's Cartesian product range adapter takes multiple input ranges and produces a range of all the ordered tuples formed by taking an element from each input. We can use this in conjunction with iota to create ranges representing multidimensional index spaces. So for example, here, we use this pattern to write a simple parallel matrix transpose. So the range V will produce two element tuples from 0, 0 to n-1, m-1. And the iteration order here will be row major, so the second index will be contiguous. We can change that to column major by switching the order of arguments to Cartesian product. So the C++17 execution policy parallel algorithms are fork-join synchronous. So each invocation launches its work in isolation and blocks until that work completes. So for example, if we invoke two parallel for eaches on the same data back to back, we're going to get two parallel work launches. The caller will be blocked waiting for the first invocation to finish, and only then will the second invocation be enqueued and launched. This transfer of control back to the caller is a latency bubble and can degrade performance. So one way to address this problem is to fuse the operations together into a single parallel invocation, which we can do with the transform range adapter. So transform takes an input range and a function, and it returns a range that is the result of applying the function to the input. So this is completely lazy. The function is only evaluated as needed when the elements of the return range are accessed. So for example here, f is not evaluated until the elements of v are accessed in the parallel for each. Now this is a big change in semantics because previously we had a guarantee that all the invocations of f would happen before any invocations of g, and we no longer have such a barrier here. But in a lot of cases, that might be fine. Another useful range adapter is filter, which takes an input range and a predicate function and produces a range of all the elements of the input for which the predicate returned true. So again, this is done lazily. The predicate isn't evaluated until the elements of the returned range are accessed. So here we use filter in combination with a parallel reduction to sum only the positive elements of a container. So let me show you some applications that have already adopted standard C++ parallelism. So Lulesh is a mini app for Lagrangian explicit hydrodynamics on an unstructured grid. It's designed to stress vectorization, parallel overheads, and on-node parallelism. And it's been ported to several frameworks and programming models, including MPI, OpenMP, OpenACC, CUDA, Raja, Cocos, and now standard C++. With the standard C++ version of Lulesh, you can get performance that matches many of the other backends, and you can build that same standard C++ code with multiple different compilers targeting multiple different platforms. So GCC, NVCC, Intel, even the Microsoft compiler. And you can run it in parallel on either CPUs or on GPUs, the same standard C++ code. Another example is STLBM, which is a lattice-Boltzmann framework written from the ground up in standard C++. And it can run on multi-core CPUs and GPUs without any code changes. It doesn't use any language extensions, external libraries, vendor-specific code annotations, or pre-compilation steps. It's just standard C++. So Maya is a code base for aerospace flow and noise simulations, and it's also been ported to C++ standard parallelism. And again, we have the same standard C++ code that we can run in parallel on our CPUs or on our GPUs. So the C++ parallel algorithms are great, but they're really just the start of the story. So they have two major limitations. First, the C++17 parallel algorithms are all fork-join synchronous. So they launch the parallel work, and then they wait until that work is completed before they return to the caller. So now, where exactly do they launch that parallel work? And that's the second problem. By design, users have no control or visibility into where the parallel work runs. So it happens in some amorphous implementation-defined execution context. That could be a CPU thread pool, a GPU stream, Grand Central Dispatch, Windows fibers, et cetera. You don't know, that's completely up to the implementations. Implementations have complete freedom, and users have essentially no control other than to say, I request that you please parallelize this if you so choose. So today, C++ has no standard model for asynchrony and no standard way to express where things should execute. But the solution is coming soon to your C++ implementation, senders and receivers, which is an asynchronous execution framework for standard C++. So let's look at a simple example. So first, we need to get a scheduler from somewhere, from a thread pool, a tasking system, a GPU driver, et cetera. To start a chain of work on the scheduler, we call schedule, which returns a sender. That sender will complete on the execution context associated with the scheduler. Next, we use a sender algorithm, then, to compose work onto the sender that we got from the scheduler. This work will be performed on the same execution context. The sender algorithm will return a new sender, which we can use to add more work onto the chain. Finally, we wait until the chain of work is completed using sync wait, which will wait until the return the value sent by the final sender in the chain. So there's three key concepts in this model: schedulers, senders, and receivers. So schedulers are handles to execution contexts. They produce senders. Senders represent asynchronous work that will eventually send a signal. They can be composed together with sender algorithms to form task graphs. And receivers process asynchronous signals that are sent from senders. So let's take a look at schedulers in more detail. So I said that they're handles to execution contexts, but what exactly does that mean? So an execution context is a resource that represents the place where execution will happen. So this could be a concrete resource like a specific CPU thread pool, a GPU stream, or it could also be something more abstract like the current thread of execution. Execution contexts don't necessarily have a representation in code, and today they don't have any exposed interface. They may have state associated with them like OS handles, memory, metadata, et cetera. Schedulers represent a strategy for submitting work to execution contexts. They are lightweight, non-owning handles to contexts. Schedulers are cheap to construct and pass around, and execution contexts are meant to hold all of the state. Multiple schedulers may refer to the same execution context, including multiple different kinds of schedulers. So for example, you might have two schedulers that submit work with a different priority to the same resource. You might even have a scheduler that dispatches work to multiple different execution contexts. We use schedulers to produce senders that will perform work on the execution context associated with the scheduler. Once we've obtained a sender from a scheduler, we can compose work on it. So now let's look at senders and how we actually compose them together. As I said before, senders represent asynchronous work. So they form the nodes of an asynchronous task graph, which may span multiple schedulers and multiple execution contexts. Senders are lazy. You must explicitly start them. When a sender's work completes, it sends a signal to the receivers that are attached to it. So receivers are handles that get notified with a signal by a sender. And there are three different handling paths, which are called channels. The value channel is used to indicate successful completion and may pass one or more values to the receiver. The error channel indicates that the sender's work failed and passes an error object that contains information about that failure. The done channel is used to indicate that the sender's work was canceled before it could be performed. Now, this is distinct from the error channel because in this model, cancellation is not an error. It may happen during the course of normal operations. So each sender will notify its attached receivers with one signal, meaning that only one of the 3 channels is invoked. So now let's take a look at how senders and receivers are actually hooked up to each other. So we're going to start off with some scheduler, which we're going to get a sender from. A receiver is attached to a sender via connect. And this is a behind-the-scenes interface that won't usually appear when you're just using senders and receivers, but if you're writing your own senders and receivers, you'll probably use connect. So connect returns an operation state, which contains the actual work that the sender represents. Eventually, you initiate the work by calling start on the operation state. And after some time, the operation completes and then notifies the receiver with the signal. Okay, now let's take a look at sender composition itself. We compose together senders using sender algorithms, of which there are a couple different forms. The first is sender adapters. So sender adapters take one or more senders as parameters, and they return a sender. Most sender adapters are pipeable, just like range adapters. So the semantics are similar to Unix shells. So send pipe f pipe g is equivalent to g of f of send. Languages like Haskell and APL call this point-free style. The primary input argument is not explicitly named. And this syntax is essential for the elegant composition of senders. So composing senders via nested function calls would be a bit of a mess because the order in which operations occur would be inverted from the order in which they appear in code. So like in this example, the predecessor senders are more deeply nested and thus appear after their ancestors. Now, things would get a bit clearer if we instead used temporary variables for each stage of the composition, but this can be pretty error-prone because it can become easy to mix up one of these named variables. So the pipe syntax gives us a clean way to compose chains of senders in the order in that which they will be evaluated. So now, let me show you some of the most important of these sender adapters. So we've already seen then, and then takes an invocable, f, and calls it with the values sent by the prior sender. The sender returned from then will send the results of the invocation of f. So this is how you attach a continuation to a sender. Now, bulk is similar to then. It evaluates the invocable once for every index in the shape n. In the simplest and most common case, the indices are one-dimensional and start at 0. And the shape argument is just an integer indicating how many invocations to perform. The sender returned from bulk will pass along the signal that was sent by the prior sender. Transfer changes the scheduler that will be used for the next sender, but it doesn't change the scheduler for the prior sender. Now, some senders can only be connected to a single receiver, for example, because they move any values or error that they send instead of copying them. And we call these one-shot senders. Now, senders that can be connected multiple times, we call them multi-shot senders. Split takes any type of sender and returns a multi-shot sender that passes along the signal from the original sender. So split represents forks in a sender task graph. This is how we introduce parallelism to a sender task graph. Conversely, WhenAll takes multiple input senders and returns a single aggregate sender that will send the signals from all of the inputs. The senders returned by WhenAll do not have a scheduler associated with them, which means they do not promise where they complete. And the reason for that is because we have multiple input senders, and it would be difficult to pick just one of them as the completion context. So instead, we require you to explicitly say where you want this to complete. So WhenAll senders represent joins in a sender task graph. Now, WhenAll is not a pipeable sender adapter because the partially applied piped form would be ambiguous with the fully applied non-piped form, as it takes a variadic number of senders. Ensure started connects and starts a sender, returning a new sender that will pass the signal sent by the original. If the input sender is a composition containing other senders, those senders will be connected and started as well. So sender factories are another kind of sender algorithm. They do not take senders with parameters, but they do return a sender. Sender factories are used to start new chains and graphs. The senders that they return are the root nodes. We've already seen one sender factory, schedule, which returns a sender that completes on the specified scheduler's execution context. The returned sender doesn't send or represent any actual work. It's just a handle that you can use to compose work on that scheduler. Just is another sender factory. It takes a set of values and produces a sender that will send those values immediately when connected. So this is how you can introduce like some values that you have into a sender graph. The last kind of sender algorithms are sender consumers. So these take senders but do not return senders. They typically launch a sender graph by connecting and starting it. So these are typically the leaf nodes of a sender graph. So sync wait is a sender consumer and synchronization primitive that blocks until a sender completes and then returns or throws whatever was sent. Okay, now let's discuss the details of how sender graphs are formed. So let's suppose that we have a single link in a chain of senders. So we're going to have some abstract before sender adapter on the left-hand side of this link, and a concrete then adapter, and then an abstract after adapter on the right-hand side. If we unroll this pipe syntax, we're going to have something like this. We've got a before sender that came from somewhere, and then we create a then sender, which will contain the before sender and the function f. We'll also create an after sender, which will contain the then sender. So we're going to end up with a nested structure of senders that looks like this. Now at some point, we will connect a receiver to the outermost and last sender. And then each sender in this nested structure will connect a receiver to its child. And this will happen in the opposite order of sender construction. And so this will give us a nested receiver structure that's the inverse of the sender structure. A nested operation state structure is also produced and returned from connect. Eventually, we're going to start that operation state. And as the operation's complete, they'll begin notifying their receivers with signals. When the before sender gets its signal, it will notify the then receiver. If it's a value signal, the then receiver will invoke f with the value and signal the after receiver with the result of that invocation. All right, now let's look at a more advanced example. So we're going to write a generic asynchronous and parallel inclusive scan. We're going to write it as a pipeable sender adapter so that it can be composed with other sender algorithms. So it's going to take 3 parameters: a sender, which will expect to send the input as a range, an initial value, and the number of tiles to split the input into. So we're going to use the classic 2-pass parallel scan approach, which requires temporary storage for partial results communicated between tiles. So we need to allocate this temporary storage asynchronously once the prior sender has sent us its input. To do that, we'll chain a then sender onto the prior sender. In the body of this continuation, we'll create a vector to hold the partial results. And then we'll return both the input range and the vector, which will send them to the next thing in the chain. Next, we need to do the first parallel pass, the down sweep. And we're going to use bulk here to invoke the body of the pass for each of the tiles. The first thing we do for each tile is calculate the range of elements that belong to the tile. Then we'll take all elements in each tile and we'll perform a local serial inclusive scan on them. And we do that right here. Next, we need to propagate information between tiles. The sum of each tile needs to be added to the elements of all preceding tiles. Now we've already computed that sum. It's the last element of the local inclusive scan that we did. And so we're going to store that into this partials vector. Now, assignments to partials from different tiles is going to happen concurrently, but that's fine because each tile uses a different and unique slot in partials, and no one reads from partials yet, so there's no data races here. Then after all the tiles have completed their local inclusive scans and written to partials, we need one execution agent to do a serial inclusive scan of partials. And we do this by piping another then sender onto the chain, which will perform the partials inclusive scan. Then this then sender will then pass along the input sequence and the partials vector. The result of the scan over partials looks like this. So now the information that each tile needs to add to its elements is in the partial slot for the tile directly preceding it. So now we need to go parallel again to distribute that information within each tile. And this is called the upsweep pass. So we're going to pipe another bulk, once again, over all tiles. In the body of this bulk, we need to calculate which elements belong to the current tile, just as we did before in the downsweep pass. And then we'll use a serial for each to increment each element in the tile by the appropriate value from the partials vector. And after that addition, we'll have the correct result for each element. Finally, we want the sender returned by our asynchronous inclusive scan to only send the input sequence, not the partials vector, because we're done using the partials vector, we want it to be destroyed now. So we're going to add a final then sender which only passes along the input. And the partials vector is going to be destroyed when this then sender completes. And that's it, we're done. We've got a generic, asynchronous, and parallel inclusive scan that we can run on any scheduler that we want. We can imagine that we'll have a whole set of asynchronous parallel algorithms based on senders and ranges. The design space for these interfaces is still open. It's straightforward for some common cases, like a series of for eaches over the same sequence. We could have an in-place transform async, which takes a sender of a range and a callable and returns a sender of a range. And then it would be easy to rewrite that series of synchronous for eaches into a lazy asynchronous operation with transform async. But let's look at a more interesting case, normalizing the elements of a range. Now we can do this by getting the maximum element of the range and then dividing each element by that one. So it's a bit more challenging to map this to asynchronous execution. The piping syntax is great when you have one dependent value that you want to pass down a linear chain, such as a single input sequence. But in this case, there are two asynchronous inputs to the second call, the input sequence and the maximum element. So perhaps we'll want asynchronous parallel algorithms to return richer senders. So for example, reductions like max element async should probably send both the input sequence that was passed to it and the iterator to the maximum element. Or maybe we want some sort of placeholder syntax that makes it more elegant for us to pass multiple different things down through a chain. So we've developed a prototype implementation of standard C++ senders and receivers that supports CPU schedulers, GPU schedulers, and distributed schedulers. And it's open source and available on GitHub. Let me show you some examples and some results from that implementation. So this here is a simple electromagnetic wave simulation that solves Maxwell's equations on a uniform grid. And this is the entire solver loop, which is expressed as a graph of senders. So this code can be run with a variety of different schedulers. By changing just one line of code, the kind of scheduler passed to the solver, we can go from running inline on a single CPU thread to running in parallel on a CPU using OpenMP, to a single GPU, to multiple GPUs within a single node, and to multiple nodes scaling up to thousands of GPUs. With standard C++ senders and receivers, you can change one line of code and scale from a single CPU thread up to an entire cluster of GPUs. So Palabos is a framework for parallel computational fluid dynamics simulations using the lattice Boltzmann method. we've ported one of its applications to standard C++ senders and receivers. This simulation models carbon sequestration techniques. So the porous structure that you see is sandstone, and it's filled with saturated salt water, which is not visible on this representation. The red bubbles correspond to liquid CO2, which is injected at the bottom and travels through the sandstone because of buoyancy forces. Using our distributed GPU scheduler, we've been able to run this application at scale on up to 512 GPUs. Senders and receivers are the next major step in the development of C++ standard parallelism. They deliver the second and third pillar of our plan. The framework gives us the tools we need to write our own generic parallel algorithms that can run anywhere and to compose together asynchronous task graphs. Following the standardization of senders and receivers, we'll introduce new asynchronous sender-based versions of the standard parallel algorithms. So now I want to sort of shift focuses a little bit and talk about algorithms and data structures beyond single dimensions, which is mostly what we've been talking about thus far. So today, C++ has no reasonable abstraction for multidimensional data. And this is unfortunate because many of the interesting compute-heavy problems that benefit from parallelism have a multidimensional shape. And that's why we're introducing Mdspan, a multidimensional span type in C++23. It's very similar to the one-dimensional span that we introduced in C++20. So Mdspan is non-owning. It's just a handle to some underlying data. It doesn't manage the lifetime of that data. And Mdspan is thus cheap to copy. It just contains a pointer and metadata describing the size and shape of the structure. Metadata, such as the extent of a dimension, can be expressed either at runtime or compile time, allowing for metaprogramming and compile time optimizations. Mdspan parameterizes how a multidimensional index is mapped to a location in the underlying data. We call this parameter a layout, and it can express any kind of multidimensional structure. There are some concrete layouts in the standard library for common use cases, but anyone can define their own layout and plug it into an Mdspan. Likewise, Mdspan parameterizes how it accesses the underlying data. The default is to just perform a normal C++ pointer dereference with an index. With the custom accessor, you could instead use a special cache bypassing instruction, read from disk, perform a remote memory access, or do a checked access. Mdspan uses extents objects to express the number of dimensions in a space, the rank, and their length, the extent. So extents objects take a variadic number of integrals as template parameters. For dynamically sized extents, the magic value dynamic extent is used as a template parameter, and the extent is passed to the constructor. Now, through the power of C++20's class template argument deduction, when you're working with all dynamic extents, you usually don't need to spell out the entire verbose instantiation. So in this case here, the E0 and E1 are declaring the same thing. E0 is just using CTAD. There's also an alias dextents for the all dynamic extents case. It takes a single parameter and integral specifying the rank, and this is useful for the places in which you can't use CTAD, for example, when you're declaring the return type to a function. For statically sized extents, the extent itself is passed as a template argument, and no corresponding constructor argument is needed. You can mix static and dynamic extents. For example, in this case, we have one static extent and one dynamic extent. So we'll need to pass just one extent at runtime. Extents objects in Mdspan support arbitrary rank. You can have as many dimensions as you want. However, that rank is static, so you have to know at compile time how many ranks you want. So Mdspan has 4 template parameters, 2 of which are optional. The first is the element type, and the second is the extents type, and this must be a specialization of the extents class template. The third is a layout, and the default is layout right, and we're going to discuss layouts more in a few minutes. And the final parameter is an accessor, which performs element access. So as I showed you with extents, likewise with Mdspan, Mdspans of all dynamic extents have a pretty simple syntax. With class template argument deduction, you can construct one without specifying any template parameters. And if you do need to spell the type out, it's pretty concise if you use the dextents alias. The elements of an Mdspan are accessed via the index operator. Thanks to a recent core language change in C++ 23, the indexing operator can now take multiple parameters, and that's what we use for Mdspan. You can also make Mdspans of static or mixed extents. The simplest way to construct these is by passing an extents object as the second constructor argument. So now let's talk a little bit more about layouts. So the two most common layouts are layout right and layout left. With layout right, the rightmost extent is contiguous, meaning that its stride is 1, and strides increase from right to left as the product of extents. This is the layout for C++ built-in arrays and for NumPy. It's also the default for Mdspan. So for example, if we have a 2x2 matrix, the two elements on the first row would have data locations 0 and 1. And the elements on the second row would have data locations 2 and 3. With layout left, the leftmost extent is contiguous, meaning its stride is 1, and the strides increase left to right as the product of extents. This is the layout used by Fortran arrays and by MATLAB. So if we had a 2x2 matrix in layout left, the two elements in the first column would have data location 0 and 1, and the two elements in the second column would have data location 2 and 3. There's also a standard layout, layout stride, that allows you to explicitly specify the strides for each extent. Now, all three of these concrete layouts in the standard library are just implementations of the layout concept. Generically, a layout is just something that maps a multidimensional index to a data location. Anyone can define a layout. Layouts may be non-contiguous. They may map multiple indices to the same location. They may perform complicated or expensive computations. And they may have or refer to state. Parameterizing layout is critical because it allows us to write generic multidimensional algorithms that can be used with any layout. This is an essential component of portability because different layouts may be needed on different platforms to deliver on performance. Today, we have a major vocabulary problem with multidimensional types in the C++ ecosystem. Suppose I write a function that uses a concrete owning multidimensional type like eigenmatrix. My users will be able to pass an eigenmatrix to this function, but what if they have a boost ublas matrix or a PETC matrix or a Blaze matrix or a Cutlass tensor or a multidimensional array that's been passed from Fortran? That's where Mdspan comes in. By using it in your interfaces, your code can work with any multidimensional data structure. Because Mdspan is just a non-owning handle, you can construct one that refers to any type of matrix, an eigenmatrix, a boost ublas matrix, a PETC matrix, etc. So for example, let's suppose we had our own row major matrix class like this. We can add a simple Mdspan conversion operator, allowing us to pass our matrix class to any interfaces that expect an Mdspan. In some more complex cases, we might have to write our own layout type. So now let's look at how we can use Mdspan. So this is a simple 3D 7-point stencil inner kernel, similar to what you'd see in a proxy application like MiniGhost. We have two 3D Mdspans representing the problem state. Using that Cartesian product of iotas technique that I showed you earlier, we build a range iterating the index space, and then we use a parallel for each to iterate that space. If we want to change the layout, all we have to do is change the input Mdspans. Everything else remains the same. So earlier I showed you this example of a simple parallel matrix transpose. We used span and we dealt with the multidimensional indexing manually. Now that's not particularly portable. We've hard-coded a specific data layout which may not make sense in all circumstances. It's also error-prone because it's pretty easy to make a mistake in the indexing formula. So we can improve this by using Mdspan instead. Now we can change the layout by simply changing the type of Mdspan that we use. Now I'm fairly happy with that last slide, but I want more down the road. I'd like to be able to write something like this. Now there's three things here that we don't have yet in C++. The first is parallel algorithm overloads that accept ranges directly instead of iterator pairs, but that's in the works. The second is an indices method on Mdspan that returns a range of its multidimensional index space. And you may have noticed that I haven't talked at all about Mdspan iterators yet, and that's because Mdspan doesn't currently have them. And if you're interested in learning more about that, you should come to my talk tomorrow. And then finally, I want a language extension here to destructure tuples and parameters. You may have noticed I've got the destructuring syntax in the Lambda parameter list here. That doesn't actually work today, but I really don't want to have to write that extra line right here. That's just uselessly verbose. Now, going a step further, I of course would want an asynchronous version of this that can parameterize where it runs, so I can have it run on my GPU and my CPU, etc. So Mdspan has a powerful slicing interface, Submdspan, and it takes an Mdspan and it returns a sliced Mdspan. Because Mdspan is non-owning and cheap to copy, slicing is also cheap. You're just creating a new view of the same underlying data. The input Mdspan is not modified. For each extent of the Mdspan, you pass a slice specifier to Submdspan. There are 3 different kinds of these slice specifiers. So the first specifies a single interface, the single index to be selected. And you do that by passing just an integral as the slice specifier. And when you do this, the rank of the returned Mdspan is reduced by 1 for each of these single index slice specifiers. You can also pass a range of contiguous indices to be selected for an extent. Finally, you can pass full extent to select an entire extent. So for example, here we have a 3D Mdspan, M0, and we make a slice of it by selecting 8 indices for each extent, starting at indices 15, 31, and 7. The Mdspan returned by Submdspan M1 will have a rank of 3. We didn't use any single index slice specifiers, which would cause a rank reduction. Each of the extents of M1 is going to be 8. Multidimensional indices for M1 will be offset from what they would be for M0. So for example, M1000 would be equal to M0 15, 31, 7. So let's take a look at another example, this time one with rank reduction. So now we're going to slice M0, selecting index 15 for the first extent, the entire second extent, and index 31 for the third extent. So the Mdspan that we produce, M2, will have rank 1. And the extent of that rank will be 128, which is the extent of the second dimension of M0. Now, iterating through this 1D slice will be equivalent to accessing M0 with a fixed index for the first and third extent. Submdspan is a useful tool for writing tiled algorithms. So now let's look at an example where we're going to build a tiled version of that parallel matrix transpose that we looked at earlier. And we're going to work with square tiles with extent t by t. So first we need a range describing this set of all tiles, and we're going to again use a Cartesian product of iotas for this. It's okay if the tiles at the edges extend beyond the bounds of the matrices. We're going to handle that in a moment. Then we're going to have a parallel for each, and this time it's going to iterate over the tiles, not all of the indices. For each tile, we need to create a new sliced Mdspan for A and B using Submdspan. So first, we need to determine what range of indices we need to select based on the coordinates of the tile. This is where we handle tiles that would go beyond the bounds of the matrices. We just truncate them to the ends of the matrices. So now we'll pass those tuples describing the indices that we want to Submdspan, producing the local Mdspans for this tile. Next, we need a range of the multidimensional indices within the tile. And we're just going to use Cartesian product of iota for that again. And then finally, we want to use a C++ range-based for loop to iterate over the indices of the tile and perform the transpose with the local Mdspan slices that we made. And with that, we're done. Now, if you want to see an even cooler version of this example, come to my talk tomorrow where I talk more about multidimensional iterators and Mdspan in a little bit more detail. So the set of standard C++ algorithms that we have today is great, but it's not complete. What we have is primarily focused on manipulating one-dimensional sequences of objects. We only have a very limited set of numerical algorithms, such as reductions and scans. We don't want C++ programmers writing their own versions of common numerical algorithms. We want them to be able to use standard interfaces that are backed by an implementation designed and optimized for the platform that they're running on. And so the C++ committee is exploring new families of algorithms to standardize, starting with linear algebra. So we don't want to reinvent numerical linear algebra. We just want to standardize existing practice. And the existing practice for linear algebra is BLAS, the basic linear algebra subprograms. So what we want is to build a standard modern C++ interface that can be implemented under the hood by existing BLAS libraries. The existing one-dimensional C++ algorithms parameterize data with iterators and send C++20 ranges. For standard C++ linear algebra algorithms, we plan to parameterize data with Mdspans instead. We use Mdspan parameters to express things that appear as distinct parameters in traditional C-style BLAS interfaces. So for example, instead of having scaling parameters on matrix vector product, we have a scaled operation that takes a scaling factor in an Mdspan and returns a new Mdspan that will apply the scaling factor upon access. Now, C++ standard library implementations can see through this abstraction and extract the scaling factor to feed it to a lower level BLAS interface that expects it. Another example is transposed, which returns a transposed version of the supplied Mdspan. So as with today's C++ algorithms, we're planning to have serial and fork-join parallel overloads of the linear algebra algorithms. Now, in this example, we're solving a system via upper triangular Cholesky factorization, and we'd really like to be able to chain these two operations together and launch them asynchronously. So in the future, we'd imagine that we'll have asynchronous sender adapter forms of these algorithms that will allow you to do just that. There's plenty of other work down the road for C++ standard parallelism. There's other classes of numerical algorithms that we should standardize. There's asynchronous streams, memory model extensions for things like distributed computing, and affinity and locality facilities, etc. But with every standard revision, we're delivering more and more components of C++'s story for parallelism. So I want to end with where we started, which is with our goal. So we need on-ramps to parallelism in standard C++. Almost all modern platforms are parallel, yet a shocking amount of code does not take advantage of that parallelism. So we want to normalize parallelism and accelerated computing. Writing parallel C++ code should be easy and natural, and parallelism should be the default, not something that we opt into. Thank you all for your time, and I think I got a little bit of time for questions. So if you got questions, we got 2 microphones here. Hi, go ahead.
Hey, thanks for the talk. I'm really happy to see C++ moving into this direction, trying to standardize those kinds of models. We've been using this in the gaming industry for the past 8-10 years, something like that. So I'm happy to see this being standardized. So exactly like the task graph and all that you're describing. I had a question regarding mostly to the extensions towards accelerators and the GPUs.
Yeah.
The key question is the vendor-specific implementations, right? It's how does that code get on GPU? How does it get compiled? I also have some questions about debugging, but mostly it's related to the vendor extensions themselves. How would they interface with our C++ code?
So I think I'm going to need you to expand a little bit on that question. So our compiler, which is the one that I can speak to, it supports both vendor-specific languages like CUDA C++ and also C++ standard parallelism, which is not a vendor-specific thing. You can use both in the same translation unit. They're ABI compatible, but I'm not really sure I understood your question.
So it's more like when I'm compiling with Clang and using this standard library, would I get the GPU acceleration?
Not right now. So Clang has an implementation of the parallel algorithms, which it's planned to have multiple backends. The current backend is TBB. Clang and GCC actually use the same implementation, which supports the same set of backends. The Intel compiler has its own separate implementation, which is also backed by TBB. Our compiler in VC++ supports both CPU parallelism using either TBB or OpenMP, and also GPU parallelism using CUDA. And then the Microsoft compiler has its own backend that is based on a thread pool implementation.
Okay, so if I want to ship a new FPGA, I would need to write a different backend for the compiler to support that.
Yeah, yeah.
Thank you.
Hey, great talk, thank you. I have two questions. The first one is, how would you differ the standard libraries versus some of the popular frameworks like Intel TBB, like you just mentioned, and also the Boost Async I/O? And the second question is, if your vision for these third-party libraries is that they're just here to die, and the standard library is just going to be replacement for these.
So what was the first question again? I'm not sure I understood the first.
How would you compare the standard library implementation of these versus the some of the popular frameworks like Intel TBB for parallelization and Boost Async I/O for asynchronous execution?
So something like TBB is an example of an execution context that you might write a scheduler to. Senders and receivers does not provide you with like a particular tasking engine. It's just a framework for expressing asynchrony that's agnostic of what execution context you're running on. We plan on having a sort of a system default scheduler that will do something that's going to be up to the implementation. We also plan on having some sort of simple thread pool scheduler that'll be in the standard library, although that will probably not be the thing that most people will reach for. It'll just sort of be like a default, like if you don't have another one. But we imagine that a lot of people will use whatever scheduler makes the most sense for their platform. So it's really, senders and receivers is more of like a protocol and an interface. It's sort of like, there's iterators in the standard library, but that doesn't mean that there aren't third-party containers, or there's allocators in the standard library, but that doesn't mean that you can't write your own allocator. In this context, something like Boost ASIO or TBB is more like a particular concrete allocator that you might want to plug in to some standard library machinery. Yeah. Any other questions? Microphone just.
Yeah, thanks for answering the first question. My second question was on the vision for the third-party libraries, but I can guess that you are saying that these are back-end implementation and they're here to stay, but you are providing a unified front-end framework that's like a thin wrapper that will aggregate these backends.
Yeah, I don't think that there's a lot of value in us standardizing a particular concrete scheduler that has the complexity of something like TBB. It would be very difficult to spec that out, and I don't know that that would be like particularly useful. I don't know how that helps us anymore. Like the key reason to standardize senders and receivers is to have it in the standard so that there's like this one interface protocol that like all libraries can use to talk to each other. Yeah.
Yeah, great. Thanks for your answering. And I see the similar spirit from the multiple dimensional arrays, like a wrapper, but there are multiple implementations. Thank you.